h of z, we could do that, and we can define it as such. It's the difference of the g0s and the difference of the g1 and the f1 inside and outside, right? But notice that what does this have? Well, where these overlap, right? Where these overlap, those are equal because they're both giving, that's how we have their equality on the overlap, right? So where these two cases overlap, they're equal, right? On the other hand, what happens at infinity? Well, we normalized both of the g1 and the f1 so that at infinity we get 0. So they also match at infinity, right? In fact, h of z goes to 0 at infinity because they're both going to infinity. So what do we have altogether? Well, we have that this function h is bounded and it's an entire, right? Why is it entire? Because this is analytic inside that radius and this is analytic outside the inner radius. So h of z is analytic everywhere. Yeah? So it's a bounded entire function, therefore it must be constant. This is Leibniz's theorem. And therefore, h of z has to be equal to 0 because, well, h of z is equal to 0 on the annulus by construction, essentially. Let's see here. How did I get this 0? All right, so I got that. Now, curse you, double scrolling. I hate the double scrolling. I hate the double scrolling so much. I hate it with a perfect hatred. All right. So then the existence of the Laurent decomposition is due to Cauchy's integral formula on the annulus. How is this? All right, so let me turn the lights back on and talk about this carefully. So let's see here, some subannulus. See if I can draw the picture. All right, so consider a subannulus. So we have the, oh man, it's still wet. We have rho inside, then we have this R here, then we have a S out here, and then we have the sigma out here. And of course the inner red and the outer green could go to 0 or infinity respective, right? So let's see here to label. This one is rho, that one is R, this one is S, and that one is sigma, right? Where is Z in this picture? So the center point is Z naught, right? And we want to consider Z where?
It's in between R and S.
Okay, so that makes Z is like some point in here, right? Between the R and the S, right? Between somewhere in here. So do you guys agree with this? What did Cauchy's integral formula tell us? Do you remember? If we have f of z is holomorphic on some region in the complex plane, right? Then the value of the function at any point in that complex plane can be reproduced by the integral of the function. I'm forgetting my 2 pi I. All right, so here's between the annulus, right? It's getting very too busy. I regret this. Oh well, it's too late. Anyway, Cauchy's integral theorem says that f of z is equal to what? 1 over 2 pi I, right? Or did I remember it wrong? No, 1 over 2 pi I, integral over the boundary of the region, right? Of what? F of w dw over w minus z, right? But for this horribly hatched region, R, what is the boundary of R? The boundary of R is given by modulus of z minus z naught equals to S, or the modulus of z minus z naught equal to R, right? But to be careful, it is what? This one has to be counterclockwise, and this is clockwise, right? Because the outer one is like that, the inner one is like that, right? Did I do it the opposite? Did I just mess it up? Yeah, I just did it exactly backwards. Counterclockwise, clockwise. See, if we had a clock in here, then maybe I would have gotten it right. But anyway, like that. So there it is. That's the formula. F of z is this minus that. The reason there's a minus there is that we want to rewrite it in terms of the counterclockwise oriented. So rather than integrate over clockwise, we just put minus to integrate over the counterclockwise, okay? And that's the, which one's that? Yeah, the S has got the plus, and the R is the inside one. It's got the minus. All right? And then the claim is that this is the F0. And how did F0 have to behave? It had to be analytic what? Inside the what? F0 is supposed to be analytic what? Inside inside where? Not the R and the S, but the other thing. F0 is supposed to be F0 analytic inside where? Modulus of z minus z naught less than sigma, I believe. Right? Am I remembering it wrong? I don't know if I ever wrote it down. Yeah, inside the sigma, and F1 is supposed to be analytic outside of the rho, right? Can you guys tell me why is that and why is that respectively analytic given those conditions? What is it? Can you tell me? Where is Z?
It's in the circle with length S, which is in the sigma.
Say R.
Yes, that is true.
It's in between the disks.
Hmm. All right, let's go on here. It's got to be something. I can't think of how to explain it at the moment. I mean, my notes just say F0 is analytic for z less than, within s units of z naught, and F1 is analytic for z greater than r. Oh, too much going on in the stupid picture. I always get hung up on this stupid point. Let's see here. So let me focus my attention on one of the issues, which is the first integral, which is what? Integral?
If z is an r,
Yeah?
both F0 and F1 are analytic within R. So, because R starts after rho it starts after radius rho, and it ends before radius sigma. So, starting after radius rho matters for F1 being analytic, and ending before radius sigma matters for F0 being analytic.
Right. Agreed.
So, what exactly were you asking?
I'm asking, how is it that we know, how do we know F0 is analytic? How do we know F0 is analytic all the way to the, see, F0 is supposed to be analytic all the way inside, like notice that F0 is analytic for, the disk of radius s, the open disk of radius s centered at s naught. But you're just arguing about f of z being analytic. Well, okay.
Wouldn't the power series just be 0, where f...
Well, you're okay. What was f0 of z was equal to what? 1 over 2 pi I, what? 1 over 2 pi I, oh. Integral modulus of, w minus z naught equal to s, right? F of w bw over w minus z. So my question is, why is this holomorphic all the way to
because of the FW instead of the F0W.
because of the f of w.
Is that what you're asking?
Maybe that's what I'm asking.
That's the discrepancy? Because it's F and W.
F of, okay, so yeah, good point. F of w is taken from the blue dotted line, right? Where we're given that f is holomorphic. So, right. I think it's just that.
Which blue dotted line?
This one here. The dark blue.
Okay. We're given that?
Well, yeah, because that's within the sigma rho annulus. Let's go on here. Let me try to finish something here. So I'll come back to these examples next time. This is what I really wanted to get to today, at least once. So suppose we have the Laurent decomposition, all right? Then by theorem 8.42, there exists a power series representation of F0, right? And so F0 can be written as a power series because it's analytic to 0, right? And so there's its power series. But on the other hand, we know that F1 is analytic where? At infinity, right? And not just that, it's normalized to be 0 at infinity, which means that if we look at F1 of Z, and this right here is using the, notice the index here, that is a fancy way of saying reciprocal powers. See, I'm going k equals -1 to minus infinity here. There's no constant term because it's 0 at infinity. So you've got F1 of Z is that, you've got F0 of Z is this. They're both normally convergent on their, they're both normally convergent, and that means they're both converge normally on the annulus, which means that you can add them together without worrying about reordering terms and stuff like that. And so we sum them both together and we get this, and this is what we call a Laurent series. A Laurent series centered at Z0 has infinitely many powers, both positive and negative in principle. In practice, it's usually the case that like half of it's 0. But what's interesting is when a little bit less than half of it's 0. More than this, we can fall back and we can figure out how to calculate the coefficients, right? And if we integrate over the circle of radius r, where that's that r, be some radius, some circle between the, some circle on the annulus of convergence. When we do that, we can trade the function for its power series, for its Laurent series, and then we do what? The usual thing. Exchange order of integration summation. That's reasonable because it's uniformly convergent, so we can interchange the order of summation integration. And then how does this integrate? Well, this is only going to be a non-trivial integral if k is equal to -1. So I express that with Kronecker delta k minus 1 times 2 pi I, which gives us 2 pi I a sub -1. So this integral is just defined simply by the coefficient of the Laurent series at the -1 power. That means that we can integrate functions by finding the Laurent series and simply selecting the coefficient of the -1 power weighted by 2 pi I. That is the entire content of the next chapter in my book. It's not my book, in my notes. A book has an editor and like errors are fixed. My notes are free. Anyway, so more than that though, see, remember what else we did? When we looked at a power series, we did what? We thought about Taylor's theorem, and we realized that, if we look at the generalized Cauchy integral formula, right? Well, we could also, that just gave us a sub -1. How about the other coefficients? Well, if we divide f of z by z minus z naught to the n plus 1, then that will shift the index a bit, and then we do the same integral, switch the order of integration and the summation, and we get a Kronecker delta, but this time only when this is equal to -1, which is to say that k has to be equal to n. So out pops 2 pi I a n, and oh, look at this, we just found a formula that a sub n is equal to the integral of f of z divided by z minus z naught to the n plus 1. Now we've seen that formula before, but when we saw it before, it was a different context, right? The context was that we could actually evaluate the derivatives of the function at the center point because we're talking about a holomorphic function. And so we had that this integral was equal to the nth derivative at z naught divided by n factorial. In our current context, f of z naught doesn't even have to be defined. You understand that the Laurent decomposition is doing something really subtle. It's giving you an expansion for a function around a point where the point is outside the domain of the function, possibly. And yet, it's telling you about the integral of the function around that point, in this sense. And so this, so here's the long and short of it. If we have a function that's holomorphic on an annulus, then it can be decomposed as a Laurent series, and the meaning of the coefficients is given by the integral of the function divided by n plus 1 around a unit around a circle in there. In the special case that the function is actually holomorphic at the center point, we can also say that this is equal to the nth derivative at z0 divided by n factorial. And that, of course, is exactly Cauchy's generalized integral formula. But this is an extension of that idea, because the reason it's an extension is, again, is because z0 doesn't even have to be in the domain of the function. And I guess we've kind of been getting at that. Like, we've already been kind of doing this a little bit with Cauchy's generalized integral formula, right? It doesn't feel entirely disconnected from problems you've already done, right? Think about it. But we will see that this does so much more. Now, as you can see, I have not yet discussed isolated singularities of an analytic function, so I'm certainly glad I did not expect you to turn in your homework on Thursday, because your homework has got problems about isolated singularities, doesn't it? Yeah, we were talking, Jack, right? So anyway, we will talk about the classification of the singularities and all that jazz on Thursday, I hope. Thank you.